Alright, if you are watching this, you are probably not a beginner. You have written code, you have built APIs, maybe even optimized a few. You have used int, float, bool somewhere in your code. But here is the truth. Most of us use variable types, which seems good. We rarely ask what is actually happening inside the CPU when we click the run button. Today, we will see from high level language semantics all the way down to the physics of the silicon. This is the hidden physics of data types. Okay, first let's talk about the most fundamental part, signed and unsigned. An unsigned integer is simple and straightforward. All bits represent magnitude. A signed integer is different. The first bit is borrowed to represent the sign, where 0 means positive and 1 means negative, while the rest of the bits represent the magnitude. Let's say it in action. Okay, here we have a C code which prints a range of signed and unsigned integers. Here I am using the 16-bit version. Let's look at the first line. Here I am using the binary left shift operation to store the minimum value of a signed integer. How? Well, I am shifting the 1 15 times to the left direction. So it will look like this. The first bit becomes 1 and the rest of the bits become 0. Now we all know that the first bit represents the sign. That means it's a negative number. But the rest of the bits are 0. So, does it mean that its magnitude is 0? Not really. In our modern computers, the negative numbers are represented as 2's complement. It's because inside our CPU, the ALU has only single hardware to perform operations on positive as well as negative numbers. So in our computers, if we represent the negative numbers as 2's complement, it's easier for our hardware to maintain the operations. Next up we have the maximum variable, where we are using the binary complement operation. So what it does is, it converts all ones into 0 and all zeros into 1. So it will look like this. The first bit becomes 0 and rest of the bits becomes 1. So 0 represents that it's a positive value and all ones represent that it is holding the maximum value. Then we have unsigned integer. Now for unsigned, we all know that the minimum value is 0 because it can't hold negative value, right? Then for maximum, we are again using the complement, which converts all zeros into 1. Now let's run our code. So this is the output, and this is the range of signed and unsigned integers of 16-bit. Okay, when we declare a variable, it gets stored in our RAM, right? But we have a problem here. The problem is our CPU can't do mathematics in our RAM because it's a passive storage. The data needs to be inside the CPU. Our CPU has its own little memory, which is also called register. The CPU must load the data from memory into a register, perform the operation in the ALU, and then write the result back into the RAM. That's how it works. Now, in 2026, most of the computers we have a CPU of architecture 64-bit. Now, what does it mean? It simply means that our CPU can perform operations on 64-bit data at once. Now that also means the registers we have inside our CPU are also 64 bits. Let's look at some popular registers in our CPU. Here we have accumulator register, base register, count register, and data register. These all are 64-bit containers. But they have a nesting design. Inside RAX, we have EAX, which is the lower 32 bits. Then inside EAX, we have AX, which is the lower 16 bits. Then inside AX, we again have AL and AH, which are lower 8 bits. It means that when we use int32 in our code, we are not using a smaller physical register. We are using the lower half of a 64-bit register. So the CPU is still working in 64-bit territory. It's just masking and interpreting part of it. That means smaller types don't automatically mean smaller hardware operations. We always work on 64-bit. Then what's the catch? The catch is when we use smaller data type, CPU uses masking in 64-bit register, which costs more CPU cycles. So smaller data type actually costs more runtime. Okay, enough theory. Let's do practical. Here we have two exact similar codes where we are performing some operations. If you see, we are using some nested loops to increase the number of operations. Both the codes are exact similar, but the only difference is the data types. Here in the left side, we have the first variable as unsigned 64-bit. In the second code, we also have unsigned 64-bit, but rest of the variables are different. These are unsigned 8-bit, this one is unsigned 16-bit, then we have two boolean variables. Next up, in our other code, all the variables are unsigned 64 bits. Well, boolean variables are actually interpreted as 8-bit unsigned variable under the hood. Okay. Now, if you observe, we don't need to bother about these operations, like what it does. It's just random complex operations I have written to benchmark the performance of our variables. We are not interested about what this code actually does, right? So let's run it. Here, both the codes are written in Go. Now I am using some flags to disable the compiler optimization because we are stupid, but the compilers are not. So they are actually going to optimize it and replace the variable data types with faster ones so that the code runs actually faster. But we need to disable it to actually see the raw performance difference. Let's compile the codes first. We have compiled this one. We have compiled this one. Now let's run. Now in Unix environment, we have a command called time. Using time command, we can see that the exact time a command takes to execute. It will take some time, so I will fast forward it because we have a lot of things to cover. Okay, so we have the result. The time taken is 24 seconds. Alright, let's run the second one. This one is the unsigned version. Time main. We have the result over here. Did you see the difference? This one took just 17 seconds and this one took 24 seconds. That means around 7-second difference. I know 7 seconds might seem a little low, but imagine you have an API where thousands of people are sending requests and you will see that this 7 second actually grows much larger. So this one actually helps optimize our code. You see the codes are exactly same. Even the output of both the codes are exactly same. Now, if you observe, we have only used normal addition, subtraction and binary operation in our code. We haven't used any multiplication or division. If we had, the result would have been different. Let's find out why. But before that, let's brush up on something. We know about clock cycles, right? For example, the latest Apple M5 Max has a clock speed of 4.61 GHz, while the Ryzen 9 9900X3D can reach up to 5.5 GHz. Now what does it mean? It means that the Apple M5 Max can run 4.61 billion clock cycles per second. In our processor, every operation requires some clock cycles. For example, binary operations like XOR, AND, complement, these are performed using basic logic gates. These are so fast that modern CPUs can execute multiple of them in a single clock cycle. Then we have addition and subtraction, which also take around one clock cycle. It's because modern CPUs use carry look-ahead adders, which can propagate carry bits in parallel. Now comes multiplication and division. Multiplication is more complex, but still it only requires around 3 to 4 cycles. Why? Well, because our ALU uses large parallel adder trees for this operation, like Wallace tree. Lastly, division and modulo. These are more expensive. They can require between 20 to 80 cycles depending on the width. The CPU internally performs repeated subtract and shift operations. It determines the quotient bits one by one. It can't fully parallelize the same way addition can. Because division hardware has to iterate through the bit width, a 64-bit division requires more internal steps than a 32-bit division. For example, If 32-bit division costs 20 to 25 cycles, then a 64-bit division requires around 50 to 90 cycles. Did you see the difference? Now you might be thinking, then 8-bit division is the fastest, right? Not at all. Remember the masking we discussed? Because of that, 8-bit division is also slower. Then which one to choose? Well, 32-bit division is the sweet spot. Alright, let's go a little deeper. Signed division versus unsigned division. Signed division uses the IDIV instruction, while unsigned uses the div instruction in an x86 processor. In this context, Intel and AMD processors use the x86 architecture. A signed IDIV uses 2's complement representation. It must check the sign, possibly convert the number to positive, perform the division, and then reapply the sign. But an unsigned div instruction skips all of that. So if you are sure that all your operations and results will have a positive value, it's always better to use an unsigned data type. That's why an unsigned 32-bit is the fastest data type for division and module operations. Alright, time for practical. I wrote two exact same codes which counts the prime numbers within a range. But I had a problem. I tried to test it on my machine, but the result shocked me. The time for both the codes are almost same. Well, the reason is I am using an Apple M4 chip. This Apple M4 is an ARM-based processor utilizing a RISC architecture. This means it uses sdiv and udiv instructions rather than the div and idv we mentioned. Because of Apple's highly optimized hardware and a different compiler, the execution time for signed and unsigned division is almost same. So for this test, we will be using the Google Cloud Console instead. But before we run our code, let's see what processor we have here. Alright, we have the Intel Xeon, which is a server grade processor, and the architecture is x86, what we exactly need. But before we run our code, let's talk about it. As I already said, both the codes are exactly same. Now the only difference is that this one is using the signed 64-bit everywhere and this one is using the unsigned 32-bit. Now I'm not going to explain the logic of it because we're not interested in it, right? I have added the division and module operation within the nested loop so that we can see the raw performance difference. So let's compile and run our code. I am using the first level optimization of GCC because we don't want it to interfere with our test. Running the code will take some time, so I am going to fast forward it. Alright, 2 minutes and 44 seconds. Now let's see how unsigned goes. Did you see the massive difference? Unsigned 32-bit just took 52 seconds, which is almost 3 times faster. This is how fast we can go by choosing the correct data type for our code. Variable types are not just syntax containers. Every time we choose a data type, we influence ALU iteration depth, pipeline behavior, cache density, SIMD packing, instruction selection. That's the level at which performance really lives. Not in frameworks, not in languages, but in physics. Now you might have noticed we don't mention data type always. For example, JavaScript. We just say var let const, then assign literally anything. Then how does it work? Well, JavaScript has a V8 engine. When it sees a value, it internally tags it with a type, which works at runtime. That's why single-threaded operations run so fast in JavaScript. It's almost like a self-correction feature of a running car. I hope you liked the video. Thanks for watching. I will catch you in the next one.